Hello, everyone. Thank you all for coming here this morning. It will be my pleasure to talk to you about how to combine two frameworks we have been hearing about so far, Apache Spark and Google TensorFlow. So just to give you a little bit of a background about what I've been doing so far, I'm a software engineer at Databricks, and I've been contributing to Apache Spark since version about 0.2. Back then, there was not really a release schedule as we do have now. And I did that while doing a PhD at the UC Berkeley. So today's talk will actually not be really about deep learning. It will be about how can we do numerical computations with Spark, and especially how can we leverage modern hardware for doing so. So if you look at if you have been doing data science using Spark, you are well aware of the fact that doing the first queries, doing the ETL transforms, usually involve manipulating a lot of data with complex objects, business objects inside. So, and these queries are really data heavy. However, when you want to use machine learning after that, the algorithms that run on it are usually much more intense for computations and do not require necessarily a lot of data movement. And furthermore, if you do SQL, then usually you manipulate complex business objects, while if you work on numerical algorithms, as typically is the case in machine learning, then these algorithms operate on very simple types. Usually it's integers, floating points operations, vectors, matrices. And it's a completely different paradigm from the SQL-heavy world. So also, if you look at the complete pipeline when you do data science and learning, you see that the ETL part is usually fairly fast, and that the bottleneck is really the number crunching part, the part where you do these heavy machine learning algorithms. And these numerical bottlenecks are really the good targets for doing some optimizations. Because if you can get the result faster, then your data scientists can have faster results. You can run more experimentations. So really, the whole point of this talk will be how can we get these numerical algorithms running faster in a distributed system. And for that, really, there are several ways to do that, as was mentioned before. Either you scale up or you scale out. So the first way really is if you start from a laptop, then you can ask your boss for fancy gaming machines with the latest hardware, and you can try to convince him that it is not going to be just for gaming, which I found is pretty hard sometimes. After that, you can move to the next stage, really, and try to use some dedicated hardware, such as GPUs, which we'll be talking about. And really, if you have an unlimited budget, and if you happen to be a large company on the west coast of the US, then you can start to develop your own chip to really solve your problem. But we won't go that far for this talk. On the other side, on another way, you can simply distribute your computations across multiple machines. And here you have a completely different set of problems that you need to solve. Because when you work on a large cluster like this, typically, you'll have some failures, and you need to account for that when you run your computations. So this is why, really, we have two different extremes here. On one side, we have frameworks that are meant to work with fleet of computers, such as Spark and Mahout, for example, for doing machine learning. And on the other side, we have all these libraries that are designed to work with GPUs or even more fancy hardware. And today's talk will be to see how these libraries tend to actually evolve naturally towards the same common ground. Because if you look into the latest releases of NLTK or TensorFlow, you will see that these libraries tend to work now with distributed computers. And on the opposite side, there has been a lot of effort in the Spark community to try to leverage more modern hardware, such as GPUs or more specialized units. So today I will talk about how to combine two of these frameworks, Spark and TensorFlow, on a project called TensorFrames. So why do we need really such projects? Well, if you look at the evolution of the hardware, you can see that the CPU now has plateaued in terms of speed, and really moving your data from the memory to the CPU is becoming now the new bottleneck. And that was the whole goal of Project Tungsten in Spark. Project Tungsten was here to write low-level code so that the processor's very complex heuristic can be then used to move data faster from memory to the computation core, run some computation, and then move on and have more efficient pipelining. But Tungsten and Catalyst right now don't really take into consideration the fact that most of the computation we run are just numerical. They are not complex logic with complex conditional branches. And we can do much better than that if we use some specialized frameworks. So this is why I'm going to talk now about how we can use existing frameworks such as TensorFlow and on specific hardware like GPUs to run these numerical computations. So if you haven't used GPUs, you may be wondering why do we need that? Well, the reason is just for doing pure number crunching, as was mentioned before, they're absolute beasts. And if you look at the latest trends, they're essentially between 5 and 10 times faster than just the regular CPUs, not only for raw numerical computations, but also for transferring data between the memory, their own internal memory, and the cores that do the operations. And programming with these libraries is really hard. And this is why now people tend to actually use higher-level frameworks, such as Caffe, TensorFlow, NLTK, and so on. And today I'll be talking about how to use one of these frameworks, TensorFlow, which is a library that was recently open-sourced by Google. And this library is very popular for doing deep learning, neural networks, and you probably heard a lot about it in the news recently for doing that. But when you think about it, it is also extremely good at running general-purpose numerical computations, because it implements all those logical blocks that you need for running all your machine learning algorithms. And furthermore, something that is interesting for us in the Spark community, it has interfaces in both C++ and Python, which mean that in theory, you can simply run it as a Python library inside your Spark cluster using PySpark. But we can do better than that. So let's see so why are these libraries really convenient for running on large data? Because really, most of these libraries are designed for a smaller data set. So if you look at what TensorFlow does, it gives you the ability to express a numerical computation as a graph, as a DAG, and then it takes this graph and converts it to efficient low-level operations. So here I have this very simple example in which I have two inputs, an integer x, an integer y, and I'm going to compute this new output here, which is simply the sum of x and 3 times y, so something simple. And the way you would express this computation in the TensorFlow world is by first saying that you have two inputs, x and y, and then you define an output from that by doing some numerical operations. And at this point, no computation has happened. You have simply described your computations. When you want to run the computations, you have to open, in the case of TensorFlow, a session, feed some inputs. So here I feed 2 values, and then you will get some output value out of it. And because you're able to separate the description of how you want to do the computations from the actual execution, it is much amenable to be used inside the framework like Spark. Because when you think about it, you can take a data frame from Spark and consider columns of the data frames, for example, x and y here, as inputs. So each of the rows can be considered as an input of your data. You can run this computation across for each of the rows and generate new data on the data frame out of it. And if you are able to describe this computation like this, then the framework should be able to take care of all the details of sending this computation graph across your cluster to run it on your hardware, and then compute a new data frame out of it. And it really fits well into the declarative model of Spark and DataFrames here. And here is actually how you would write it using the TensorFrames binding between TensorFlow and Spark. So actually, just to show you how it works, let me give you a small demo example. So here I have a cluster running on Databricks, and I'm going to create this small data frame containing just ranges of numbers, x and y. So 2 ranges, x and y's, and of course we can display it. We can see the content here. So x and y have these ranges of values. And if I want to use TensorFlow on this data frame, here is how I could do it. So first I import I import TensorFlow, and I import the TensorFrames binding. And then I can ask TensorFrames to give me the TensorFlow representation of what is inside this data frame. So here I can query I can query the data frame to ask what is the x column as in terms of a numerical representation. So here, TensorFrames tell me that it contains x and y. And it can infer that the shape of these elements is empty, which means it's reals. Then I can run here then I can define a graph based on these inputs. And so far, no computation have happened. And then I can take my data frame, map each of the rows of this data frame with this graph of computations. And this will create, let's see. So this will create a new, a new data frame. And now you can see that it inferred that the data frame contains, now the data frame contains a new column containing the output of the computations. And so, as usual, nothing happens up to now. And when I run it here, when I try to display it, then this is when actually it triggers computation. It loads the TensorFlow library across the cluster, runs all the computation across the machines, and then returns back some of the results. Can you switch back to the presentation, please? Okay, so how does it do in terms of performance? Well, you could consider, so one way to implement this could be simply to take the Python library, send it through PySpark, run the computations, and then get back some results. But if you do that, you'll have actually some fairly bad performance. And the reason being that if you look into how this is implemented in the background, it would take the data being represented in this off-heap binary format by Spark. It would have to convert it to raw objects, which are Java objects. Then it would have to convert them to a Python object to send it to the Python process. The Python process would receive them and convert them now to this format in a C++ buffer that then TensorFlow can consume. And of course, this is fairly inefficient here. So what TensorFrame does is that it embeds the TensorFlow library as a jar file, inside the jar file, and inside the process being run on the executor. So then you completely bypass on the executor the Python step. Even though you express your computation using this high-level Python interface, this all gets, under the hood, this all gets transcribed into protocol buffers that describe your computation, and it can directly convert the data under the hood on the executors. So how does it work really let's see how it works really in practice. So I took a small example here, which is coming from the machine learning community, and it is a kernel density estimation. So at a high level, it corresponds to taking a distribution of sample data and trying to make an estimate of the statistical distribution of this data by sampling some points and smoothing these points around by a small Gaussian. And usually when you want to do that, you need to adjust a parameter. So there is a scoring step. And it's a fairly standard technique for in machine learning. So, okay, my advisor told me when I was in PhD, Tim, if you want to be taken seriously in a presentation, you have to have a slide with some math. So here's a slide. And but really, you don't need to understand really the math behind. But what we're doing here, that we're computing a score on each of the points of this distribution. And when you look at this function, it is simply a function with all the math that you have seen in high school, with sum, squares, square roots, exponential, logarithms. So nothing dramatic. It's just a big numerical function. And if you are a data engineer and you are asked by your data scientist to implement it in your cluster, so you'd probably pick Spark, because you'd probably pick Scala, because it goes faster. And you'd probably write some code like this. So this is how you would implement this function here. And just to make sure we're comparing apples to apples here, I ran the computation on a number of points on a cluster using some high-end compute-intensive machine on Amazon, just to make sure that we compare at the end the overall cost of running the computation, not the runtime, because we need to, otherwise we cannot really compare GPUs and CPUs. So this is probably the code that you would write. And every seasoned Scala programmer here would say, this is terrible. This is not how you write. This is not how you write mathematical code in Scala. The reason being that here this uses all the high-level abstractions that are really bad for performance in Scala. So you could rewrite this code, and then by unrolling some of these constructs, and you start to get something that looks like this, which is a bit more in Wildy, but you get a significant jump in performance here. So it could cost, to run the same computation, if you unroll it, it could cost about 30% less than your basic computations. And it's a good start. It's hard to, after that, to see also what the intent of this code is going to be. So you could also, if you use TensorFrames and TensorFlow, you could write the same computation. And here I'm using some of the high-level operators that are provided by TensorFlow. And it's easier to see what the computation is doing, but also it's about the same performance just on a regular CPU cluster. So you are just, already here you're having a gain of having something more readable for nearly the same speed. And now, of course, because we're using TensorFlow, we can always say, what happens when I want to use a GPU cluster? And if you want to use a GPU, then in TensorFlow it's very easy. You just have to say, well, run all these computations on a GPU, and that's it. And here you can see really dramatic gaps in terms of performance. So really, this is the so I hope so. Mostly with this slide, I want to convey to you that this is an example here, but a lot of numerical computations can also benefit from this kind of transformation. And mostly, if you go from here to here, already you can see that you gain simply in readability and debugging abilities. And after that, really, the GPU is really the icing on the cake, in which you can simply turn it on, and then you can see what it gives to you. So, of course, this project is far from being done. And what else do we have in store? So, as I was mentioning, a lot of time is still spent on communication here, and so right now we still have this conversion here to a Java object in between. And really, what we would like to do is directly take the data from its binary representation in Tungsten and directly copy it into the C++ buffer that TensorFlow can then process. And later, in the future releases of Spark, more and more data will be stored in a columnar storage. So instead of storing the data row by row in memory, it will be stored directly by columns. And in this case, it corresponds exactly to the structure that you'd expect from a mathematical perspective. And in this case, you can directly copy all this data to to TensorFlow without having to do some arithmetic step of figuring out which pieces you want to move around the memory, which can dramatically improve the communications. So there are some early prototypes to show the improvements, but they are not ready to be shared yet. And OK, so direct memory copy and Condor Storage. And also the big step, of course, is to see how we can combine this with MLlib and how we can make MLlib leverage some of these techniques here. So as a conclusion here, we all know how Spark is efficient for running computations on large fleet of computers. And TensorFlow has been instrumental in showing how you can write high-performance numerical data and code without having really to go to the low-level nitty-gritty details that are necessary in general. So really, why not try to get the best of both worlds by combining TensorFlow computations and on DataFrames in Spark? So of course, you can try all this demo yourself. The code is open source. And on the Databricks website, we have also a couple of notebooks that show you how to run this. And of course, there are many more examples that you can run from the TensorFlow website. All right, thank you. And I'll be happy to take some questions now.
So we do have some mics set up here and here. If you would like to ask questions, those will be available. If you're in the front and it's difficult to get back there, I can also just run up. If you are using those mics, I'll remind you, please get very close to the mic as they don't pick up from a very far distance.
All right.
Okay, I can start. Thanks first for your great presentation. And I wanted to ask a question about deep learning and neural nets. Mm-hmm. I don't know if you have this in mind, and if you plan at some point to have a high-level APIs that could do this. And also I wanted to ask you about deep learning for J, and if you can compare your solution to this one. Thanks.
Yeah, so for the first question about deep learning, for now the approach has been to focus on what I feel is a need in Scala and Spark in general, which is to run some computations which are not necessarily deep learning, because here it's an easy way to do that without having to write code in Breeze or other libraries like Netlib and so on. As far as deep learning goes, there are already a couple of excellent frameworks like Caffe on Spark with and deep learning for J to do that. Of course, I would love to see this product moving in this direction. And yeah, for now, I don't have a comparison directly against deep learning for J. However, this project relies on Java CPP, which is one of the projects sponsored by SkyMinds, so one of the authors of deep learning for J, if I understand correctly. So, but yeah, I would love to see more comparison in that.
Hello. So thanks for the very nice presentation. I have two questions. So the first one was regarding a slide that you showed in the presentation, which was the performance of TensorFlow on CPUs and on GPUs. The y-axis was normalized cost. What is normalized cost?
Yeah, so here, so I run this computation on a fixed size of the data frame, which contain a number of points. And then I ran it on a cluster of 4 machines. One of them was, I think, C2, I forgot which one, C2 machines on Amazon. And I simply looked how long it took for the computation. I measured and scaled it by the cost of the machines. And I did the same thing for the GPU cluster, just to make sure that it compares exactly the same wall clock cost for running on this cluster.
Okay. And the second question, are you aware of any efforts for TensorFlow also to be available for Scala?
Yeah, that's a great question. So as far as I know, I'm aware of efforts in, let's see, Julia, Haskell. I'm not sure, Java, I think. I don't think there is quite the DSL for Scala yet. So for Scala, you can directly write the protocol buffer by yourself. It's not a nice experience, mostly because a lot of logic has been implemented in the Python framework, and especially, for example, all the automatic differentiations and the gradient building. So right now, the problem with any other language compared to Python is that Python contains a lot more things before talking to the low-level primitives in C++. and you would need to reinvent and reimplant a lot of this logic in any other language. So the TensorFlow team is aware of that and is trying to move as much as they can inside the C++ side to exploit the same API across the languages. But so far, there is not really a good solution. TensorFrame itself includes an extremely tiny DSL that runs a few matrix multiplies operations, simply to run, mostly for doing testing. But I would not call it production ready by any means.
OK, thank you.
Yes?
So you are running one executor per physical machine, and each one is launching an instance of TensorFlow, right?
Mm-hmm.
So I'm wondering, how do you combine the individual result of each instance of TensorFlow, I mean numerically? You have some methods to do that?
Yeah, that's a good question. So actually, there are really two parts here. So the first part of the question was how you can combine TensorFlow on an executor, especially now that we are moving to hardware that has multiple GPU cards. So far, the assumption has been that your computations are running long enough that you can make use of all the hardware on this machine without trying to share it between multiple tasks. So right now, it assumes only one task running per executor at a time. As far as combining results is concerned, this actually, the TensorFrame projects include a UDAF, so a user-defined aggregator function, that lets you run also TensorFlow programs that takes two similar inputs, combine them in the same output, and it will run it across aggregation until you get the final results.
So it gives you back a data frame.
So it can give you either you can use it so you can use it as a regular aggregation function. So you can either use it as a reducer to get a single point result, or you can use it inside a group by operation inside a data frame. Okay. It's available in both.
Okay, thanks. One other.
Yeah.
Yeah, so few questions. The first one is the TensorFlow CPU. Did you show result with like the netlib Java version? Because it looked like a block computation. So did you also try to represent it as a block computation with like netlib Java and did those comparisons, or? Yeah,
that's a good question. So yeah, in this example, yes, I just run I just wrote some codes using some basic Scala without trying to use netlib or some other frameworks. From experience, yeah, you could see actually some improvements in the performance here. That being said, you still had tremendous improvement when you directly use GPUs. So so in this case, you would compare actually the performance with what you would have just by running TensorFlow on CPU. It's about the same performance in this case.
Okay, and the second question is that TensorFlow also comes up with a gRPC version to distribute the computation.
Yes.
So did we make use of those in this? Or
so no, that's a great question. I haven't used the distribution framework of TensorFlow. One idea that needs to be fleshed out is to use Spark to do all the batch operations, let TensorFlow take over the cluster for the duration of the large TensorFlow job, and then TensorFlow can do some interconnect if it wants to, and then take over the cluster once it is finished. So there are a number of technical challenges for doing that, and I think a number of people have some ideas in this room on how to do that. Okay. So it's definitely something that I would like to do in the future.
Sure. Thank you.
I think we can take one more question, I believe.
It's about the memory buffer copy. Mm-hmm. You said that you are moving to Tungsten to C++ TensorFlow buffer, and then you shown a slide about columnar storage. So what is that? Yeah, so if you look into the latest release of Spark, Spark had the ability in some cases, mostly in the inputs, to not to store the data row by row, but to represent the data column by column, which is why it's called columnar storage. So instead of having, for example, in the case of X and Y here, instead of having pairs of contiguous pairs of elements, it will represent one vector containing all your X's and then one vector containing all your Y's. And that means that then it can pack them efficiently together. And in the case of numerical computing, this is really nice because then you can directly take a big buffer containing all your numbers and directly move it to another
to the other framework. So the problem right now that in terms of performance is that if you want to copy all this data, you need to go on each row and manually and say for each of the elements do a memory copy operation to move it to the other place. And this is not great from the perspective of memory management for the CPU. Because if you can tell to the CPU, I want this whole buffer to be moved to this place, or to be copied to this place, it can run much more efficient operation for doing that, rather than being told, OK, I want to move this piece, and then that piece, and that piece.
Okay.
So that's why it's, that could lead to significant performance gains there, especially for small operations. Yeah, so I think...
All right, let's give Tim one more round of applause here.
Thank you.